This presentation, Oracle Multitenant, rock solid, covers many important topics in the category of high availability, or HA, with Oracle Multitenant. I'll set the scene with an overview of the multi-tenant architecture and its key benefits. Section 2 gives an overview of PDB lifecycle management with a demonstration to pique your interest. For the technically minded, Section 3 pulls back the covers to explain what's going on during a hot clone. No HA presentation is complete without discussing DataGuard, the theme of Section 4. Next, in Section 5, we introduce refreshable PDB switchover. Integration with rack is covered in Section 6. 7th, we discuss the snapshot carousel, which provides a simple yet powerful point-in-time recovery capability. The 8th topic is transportable RMAN backups. Oracle Multitenant delivers the full promise of the database cloud: isolation and agility with economies of scale. Applications run unchanged in self-contained pluggable databases, or PDBs. PDBs are simple to clone and to move to and around the cloud. A container database, or CDB, consolidates many PDBs. Patch the CDB and fix all the PDBs it contains in a single stroke. That's operational efficiency. The shared infrastructure model is highly efficient, so you can support more applications per server. That is technical efficiency. There is a fourfold value proposition of multi-tenant, and I like to check these benefits off on my fingers. 1. We minimize capital expenses, because we can consolidate more applications per server. 2. We minimize operating expenses, because we can manage many as one. Deliver standardized procedures and services, and enable self-service provisioning. 3. We maximize agility through rapid provisioning, portability through pluggability, and scalability with RAG. And 4. It's easy. Easy to adopt, because applications run unchanged. Easy to use, because SQL is the interface. I think of the progression through the life cycle of a PDB as a bit like shifting through the gears of an old-school, four-on-the-floor roadster. You start with development, shift up into user acceptance testing, and next have to do some rigorous performance reliability and scalability testing before you're up to speed and ready to cruise along in production. Of course, you need to downshift too, for example to take a copy or a clone of a production database, perhaps as a test master or a development master. A key requirement throughout is agility in the provisioning and management of pluggable databases, or PDBs. It's extremely useful to be able to take a clone or a copy of a PDB, but there's far more to cloning than that. What's illustrated here is a typical lifecycle management, or LCM, situation in a hybrid cloud configuration. There are 3 production PDBs running in a highly efficient, consolidated environment on premises. Development and testing has shifted to the cloud. The requirement is to set up a golden master database in the cloud from which members of the development team can provision their own isolated environments. Let's consider the requirements in turn. The fundamental capability here is online cloning, also known as hot cloning. In the context of this presentation, high availability, the key thing is to set up the golden master without taking an outage in production. This is why it's so important to be able to do a hot clone, taken while the source PDB is still open read-write. Individual developers can provision their own snapshot clones from this golden master. Based on copy-on-write technology, these are highly storage efficient. They require negligible incremental storage and can therefore be provisioned very rapidly. Here, the high availability angle is the ability to create and destroy and recreate individual development environments very rapidly without impacting other developers. Refreshable PDB builds upon hot clone. Let's continue our discussion of the development and testing use case, in which one of the development golden master databases is a clone of production. Production databases tend to be large. The larger they are, the longer they take to copy. If your production database is in the tens of terabyte scale, it will take in the order of days to copy it. You don't want to do that sort of thing very often, and therefore development copies of this sort of production database tend to be rather stale. The staler the database, the less relevant it is for development purposes such as debugging. That's why we built refreshable PDB. Step 1 is to take a hot clone. That takes as long as it takes, hours, days, whatever. It doesn't really matter how long it takes, since it doesn't involve an outage in production. Now, as the clone becomes stale, we can refresh it. We do this by applying all the transactions that have accumulated since the last refresh. Even if the source database is enormous, this incremental set will typically be much smaller. It's therefore going to be a much quicker process than the initial hot clone. Therefore, it's going to be much simpler to keep your production clones refreshed with recent data copied from production. The clone may be refreshed either manually or on a specific schedule, perhaps every 24 hours. The relevance of this capability, from the perspective of high availability, is the availability of freshly updated data from production in the development master. An invaluable capability for rapidly debugging data-specific bugs. Now we shift gears back into production to discuss online PDB relocation. Why do you want this? You want this because we want this. We needed this capability for Oracle Cloud database services, including Autonomous Database. I'll tell you why. Service Level Agreements, or SLAs, typically feature two conflicting aspects: performance and availability. If a database is in danger of violating its performance SLA, the solution is typically to move it to a server with more available processing power. However, to do so traditionally involves an outage in the application, and this is likely to violate the availability component of the SLA. So the high availability requirement is to be able to relocate a PDB between servers without taking an outage. This is possible with online PDB relocation. Under the covers, we create a refreshable clone, top it up with the latest changes, and transparently switch connections. When that's complete, the original PDB is dropped. It's all accomplished with a single SQL statement. Seeing is believing. So let me demonstrate online relocation to you, so that you can understand quite how powerful a capability this is, and how simply it's performed, literally at the touch of a button. I'm going to switch to another window to demonstrate this to you. The lower main part of the screen is SQL Developer. In the left-hand panel, we see connections to our Arizona data center and to our PaaS estate in the Oracle Cloud. In the cloud, we have a PDB named Invoices, and on-prem, we have Inventory, OE, and Sales. At the top of the screen, we see a workload being applied to the OE PDB. These lines show response time for various business transactions. I'm now going to relocate that PDB to the Oracle Cloud without taking any downtime in the application. Specify the database link to the Arizona data center, select the OE PDB to relocate, enlist some parallel processes to optimize the transport of the PDB. 128 should do it, and we're ready to go. Notice that as the PDB is migrated to the cloud, the application keeps loading data without interruption. This is a hot clone. When the files have been copied, we need to apply some incremental redo to catch up with a live application. Only then are we ready to switch the connections transparently to the cloud-based container. Notice the brief pause here while connections are drained from the source PDB and re-established in the cloud. Notice also that the application doesn't fail. These connections spin briefly until we're ready to open read-write in the cloud. Okay, the relocation is complete. Now we see the OE PDB in the cloud-based multi-tenant container database. And when I refresh, note that of course it's gone from the Arizona data center. And here in OE, now in the cloud, processing resumes as if nothing had happened. But a lot did happen, although all I had to do was push a single button. What I didn't have to do was suffer an application outage. I didn't have to change my application. I didn't have to change any connect strings. It just worked. This section of the presentation is for the technically minded, to explain what's going on behind the scenes during a hot clone. First, we need to explain what's involved in a cold clone from a technical perspective. A cold clone is a relatively simple operation to understand. The source PDB must be in a quiescent state, hence the term cold clone. Basically, you close it and reopen it in read-only mode. In this state, there are no incomplete transactions and all blocks are flushed to disk. Performing a cold clone is therefore simply a matter of scanning all the blocks of the source and copying them to the destination. Even this is a sophisticated operation, however, as parallel slaves will automatically be invoked to optimize performance. Once the clone is complete, the source PDB can be reopened read-write for processing to resume. So we can do cold clones. Why not just do hot clones? It's easier said than done. I shall explain why. Before we get into that, let me illustrate what is going on in a database which is open read-write. Here we use color coding to show the passage of time, as illustrated by the clock in the upper left corner. So in the first time interval, we could think of this as yellow time. We see some data changes in blocks scattered throughout the data files on disk. Corresponding to this, we have undo segments in the undo table space, and of course redo segments written to the redo log file. Each of these changes is color-coded according to its time interval, in this case yellow. Notice that some of these changes, data file blocks, undo and redo, have check marks. These indicate that the change is associated with a committed transaction. Now, as we move into brown time, we see more changes. Notice that one of these changes is to commit a transaction that began in yellow time. All of this is summarized in the legend on the right side of the slide. We can now watch the database activity proceed as we progress through slate, steel, and charcoal time. The point of all this is that in general, we must assume that this sort of activity is going on in a database which is open read-write. That is, transactions are changing data blocks scattered throughout the data files, and it is not reasonable to assume that at any time there are no uncommitted transactions. Hot cloning needs to take account of all of this activity. With all these changes going on, it is hard enough to guarantee that the clone be physically consistent with the source. However, what is required is that it be transactionally consistent with the source as well. Incidentally, this is why it's very important not to rely on storage-level replication technologies alone to clone your databases. If you do so, the operation will appear to complete successfully. However, there are likely to be some transactional inconsistencies. Now that we understand the challenges to be addressed by an online, that is a hot clone, let's see how it works. Again, we'll use color coding to illustrate the passage of time. We begin the online clone operation in yellow time. As with the cold clone, we do a parallel scan of the data files. In this illustration, during yellow time, we can scan the first two rows of blocks as shown. These are read and copied over to the target. So far, everything is okay. All changes made to blocks in the source that we've scanned so far are copied over to the target. Now, as we run into brown time, we scan the next set of blocks. Again, there are some changes made in brown time that are picked up by this scan and copied over to the target. However, there are also some changes made to blocks which were previously scanned. These changes are therefore not reflected in the target. And now we can proceed through the slate, steel, and charcoal time intervals. As before, we see that some of the changes made in the primary during the cloning operation are reflected in the target. However, some changes made to the primary during the cloning operation happened after those blocks were scanned. Those changes are not yet reflected in the target. Here we see, with the red X's, the blocks in the target in which the corresponding block in the primary has been changed, but that change is not reflected in the target. So far then, we have copied all the blocks from the primary to the target, but because the primary was changing while the blocks were being scanned, what we might refer to as a fuzzy read, the target is not physically consistent with the primary. The next step is to fix that. This is done by copying over all the redo that has accumulated since the cloning operation began, scanning it, and applying all those changes on the target. The result of that is a physically consistent clone on the target. However, note that not all the transactions in this physically consistent clone are committed. It is now necessary to roll back any uncommitted transactions. This is done by applying the undo corresponding to those uncommitted transactions. When this is complete, the clone is in a transactionally consistent state. The relevance of all of this from a high availability perspective, of course, is that hot clones allow cloning operations to be performed whenever necessary without incurring an outage in the source system. In this section, we cover some important considerations for provisioning of PDBs in high availability configurations protected by DataGuard. Two familiar technologies cover both extremes in terms of data replication. At one extreme, DataGuard, or preferably active DataGuard, can be configured at the CDB level. This is a great example of managing many as one, and thus reducing operating costs. Configure this once at the CDB level, and DataGuard will replicate transactions from primary to standby for all PDBs in a single stream. Some granular control is possible to the extent that a PDB may be configured with no standby, where appropriate. At the other extreme, for replication of data at the individual PDB level, Golden Gate is the perfect choice. With Golden Gate, it is possible to have bidirectional replication between CDBs, as is shown here. This can even be used in an active-active configuration, which is a key capability for supporting a truly zero downtime upgrade. Important considerations apply to certain forms of PDB creation in DataGuard configurations. Two of the most common provisioning operations, creating a new PDB from seed and creating a local cold clone, work absolutely fine with DataGuard. Let's walk through an illustration of this to understand what's going on. Here we see a high availability configuration with a primary CDB at the top and a standby CDB at the bottom, with replication managed by DataGuard. We begin with a new CDB with no customer-created PDBs. Only PDB seed is present in this initial state. When we create a new PDB from seed, the create PDB operation replays successfully on the standby. This is possible because PDB seed, including its data files, is already present on the standby. The new PDB is created successfully on both the primary and the standby. Similarly, a local cold clone, that is, a clone of a PDB already present in the primary and open read-only, will succeed and replay successfully on the standby because it is already present in the standby, including all the data files necessary to process the operation. However, for various reasons, some other provisioning operations are more complicated. For example, a hot clone, that is a clone of a PDB performed while the source PDB remains online, in other words open read-write, is complicated by the fact that there are two recovery operations involved at the same time. One is to ensure that the hot clone itself is transactionally consistent, as we saw in a previous section of this presentation. The other is the application of redo on the standby performed by DataGuard itself. These two recovery operations would interfere with each other, and to avoid that, a hot clone to a DataGuard primary will have no standby replica. This may be viewed as the functional equivalent to including the clause standbys equals none in the hot cloning operation on the primary. For the purposes of this discussion, a remote cold clone, that is, a cold clone of a PDB in another CDB, is comparable to a plug-in of an unplugged PDB. In both cases, unlike creating a new PDB from seed or performing a local cold clone, by definition, the data files for the newly created PDB are not already in the CDB. Therefore, the complication in these cases is that not only do we need to copy the data files for the new PDB into the primary CDB, we also need to copy them onto the remote CDB. With these considerations in mind, we introduce some special procedures to ensure smooth provisioning of PDBs in DataGuard configurations. These involve some additional one-time steps in the process of setting up the DataGuard environment, and a simple procedure to follow in each of these somewhat more complicated provisioning cases. Let's discuss the additional one-time steps involved in DataGuard setup. We start by creating a self-referencing database link on the primary. This replays successfully on the standby to create a database link referencing the primary. Next, we set a parameter on the standby. This is named standby PDB source file DB link, and it should reference the database link created in the previous step. Finally, CDB root of the standby should be opened read-only. Note that no active DataGuard license is required if only CDB root is opened read-only on the standby. This allows DataGuard to read the value of the parameter just specified. When a create PDB operation is replayed on the standby, but the required data files are not already present on the standby, these data files may be copied from the primary via this DB link. Now we introduce a simple new procedure employing what we refer to as a transient no standby PDB. Following this procedure ensures that even these relatively complex provisioning operations can be achieved in a few trivial steps. For example, let's say that our intention is to plug in an unplugged PDB or to perform a remote clone. We want this new PDB to be named PDB3. We start by creating what is referred to as a transient no standby PDB. To do this, simply include the clause standbys equals none in the create pluggable database statement. The result of this is that on the standby, the transient PDB will be visible in mounted state, but its data files will show as offline. Next, we create the desired PDB, PDB3, as a local cold clone of the transient no standbys PDB. This replays successfully on the standby by copying the PDB's data files across the database link identified by the parameter standby PDB source file DB link. The transient no standby PDB may now be dropped. So what seemed to be a relatively complicated procedure is reduced to this simple 1, 2, 3. Follow this same simple 1, 2, 3 procedure for hot clones in high availability configurations protected by DataGuard. As before, the first step is to create the transient no standby PDB, this time as a hot clone. Again, it's important to include the clause standbys equals none in the create pluggable database statement. Remember, the intention of a hot clone is to take the clone while the source remains online. Of course, this is consistent with our high availability theme. and clearly this requirement is met in this case. Next, we create the desired PDB, PDB4, as a local cold clone of the transient no standbys PDB. This replays successfully on the standby by copying the PDB's data files across the database link identified by the parameter standby PDB source file DB link. The transient no standby PDB may now be dropped. As you see, we can use this same simple procedure employing the transient no standby PDB technique for provisioning operations in environments protected with DataGuard. The refreshable PDB switchover capability allows us to define replicas on a per PDB basis with only 2 CDBs to manage. We might start by creating a PDB named red in CDB1, and then simply creating a replica of this in CDB2 using the familiar refreshable PDB syntax. We might add a few more PDBs, green in CDB2, gold in CDB1, grey in CDB2. No replicas are required for green and gold, but we want one for grey. And as simply as that, we have 2 pairs of replicas being refreshed in opposite directions between these 2 CDBs. Now we come to the refreshable PDB switchover capability. There are several ways in which this can be very useful. For example, planned switchovers can be very helpful for load balancing. These resource meters show uneven load distribution between the 2 servers. The role transition is executed as follows. Connect to the current primary. You may find it helpful to think in terms of connecting to the future replica, and issue this statement: alter pluggable database gray, refresh mode every 2 minutes from gray at dblink, switchover. The syntax to set up the refreshable clone is familiar, and here I introduce the new keyword switchover. User connections will now be to the new primary, now in CDB1. In this example, we've seen how trivial it is to perform load balancing with this capability, while maintaining a replica on a remote server, just in case. In situations where the primary PDB fails for some reason, we can switch over to the replica and resume operations there. We refer to this as an unplanned switchover. The 3 steps to perform the role transition from replica to new primary are as follows. Perform 1 more refresh of the replica. Remember that, although the source PDB is no longer available, the refresh process involves reading redo from the primary CDB's redo stream, online redo log and archive redo log files. For the purposes of this discussion, we assume that the source CDB, including its redo stream, is intact, and that the failure is confined to the source PDB alone. Therefore, it is reasonable to assume that this final refresh will succeed. What it achieves is to transport and apply any transactions that were performed against the primary between the previous refresh and the PDB's failure. Alter the surviving replica so that it is no longer a refreshable PDB. Open the former replica read-write so that it can be used as the new primary. Let's consider the high availability implications of this capability. In the sense that it can be used to maintain a replica in another server, we've seen how a refreshable PDB may be used as a replica on which operations may be resumed, whether the switchover is a planned or an unplanned event. In that sense, it's worthwhile to consider the characteristics of a switchover from the point of view of recovery time objectives, RTOs, and recovery point objectives, RPOs. Recovery time objectives consider how long it takes before operations can resume in the event of a switchover. In other words, how long is the outage? The point is that RTO is affected by the amount of redo to be applied. In turn, that is a function of the rate of redo generation in the source PDB and the frequency of refresh of the replica. The worst case is a failure of the source just before the next refresh was due to have occurred. Assuming a relatively steady rate of redo generation at the source, this situation is likely to result in the maximum amount of redo to be applied to the replica before a switchover can be completed. In general, a relatively high frequency of refreshes, of the order of every couple of minutes rather than every few hours, is likely to leave relatively little redo to be applied before a switchover can be completed. It is important to test thoroughly with realistic transaction volumes to ensure that the process of refreshing the replica can keep up with the rate of redo generation. Recovery point objectives apply to how much data is lost in the event of failure of the primary. In many cases, the failure of the source PDB alone will not cause any data loss. As long as the source CDB remains operational, all committed transactions should be protected in the online redo logs and archive logs of the source. It is therefore likely that even transactions that had not been applied to the replica at the time of failure of the source PDB can be recovered and applied to the replica before switching over to that. The worst case is a total failure of the source CDB or its host server. In this case, the online redo logs, and potentially even the archive logs on that server, are inaccessible. With the basic refreshable PDB capability that I've described so far, there is in this and similar situations the possibility that all transactions that happened on the source since the last refresh will be lost. For example, if the refreshable PDB had been created with this statement, create pluggable database myPDB from myPDB at dblink, refresh mode every 2 minutes, the maximum data loss is 2 minutes of transactions. This assumes that the refreshes had been able to keep up with the rate of generation of redo from the source. However, another strategy exists through integration with a DataGuard remote redo repository, a component of DataGuard FastSync. This possibility arises because the refreshable PDB can read data either over a database link from online and archive redo logs on the primary, this is what we've seen so far, or from a remote redo repository maintained via DataGuard's redo transport. This slide illustrates how this works. Here, DataGuard is the only component involved in scanning redo logs on the primary and transporting them to a remote redo repository. Having defined the refreshable PDB as before, we now modify it to be refreshed from the remote redo repository. This second option has several important advantages. It minimizes the impact of scanning redo logs on the primary. It minimizes the amount of redo transport between CDBs. It enables near zero data loss in a failover situation. It may seem paradoxical, but high availability and disaster recovery are not necessarily the same thing. Let me explain. Online PDB relocation allows a PDB to be moved between servers without taking an outage in the PDB. However, we've also seen that moving a PDB into a CDB protected by DataGuard can be complicated because we also need to consider setting up the corresponding replica in the standby CDB. We could relocate the PDB into the DataGuard primary with standbys equals none, but then by definition there would be no standby PDB. So in this case we'd have a high availability, or HA, relocation, but a vulnerability from a disaster recovery, or DR, perspective. On the other hand, the transient no standbys PDB technique can be used to set up that replica, thereby ensuring that we have DR. However, since this technique involves cold cloning, it is not a high availability operation. Therefore, in this case we have DR, but not HA. We want our cake and eat it. To resolve this dilemma, we can use refreshable PDBs. Let's say we want to migrate PDB red from top to bottom, as shown here. we start by creating a refreshable PDB in the CDB to which we wish to relocate. Of course, this serves as a replica for DR purposes. If the top CDB fails, we can recover using the replica in the bottom CDB. When we're ready to relocate, we execute a switchover. The associated role transition achieves the desired result. The red PDB is now in the bottom CDB as a primary. Its replica in the top CDB can be used for failover purposes in the event of a disaster. Multitenant is closely integrated with Oracle Real Application Clusters, also known as RAC. RAC, of course, is an architecture that provides great scalability, as well as great availability. In this section of the presentation, we'll see both of these benefits. Let's start by setting up a basic 2-node RAC cluster for a single CDB. There is a single database instance per node in the cluster, and of course storage is shared between the nodes. Now let's think about the PDBs in this CDB. Here we see PDBs 1, 2, 3, and 4. We begin by discussing the topic of affinity. In other words, in which node or nodes of the cluster is each of these PDBs open? Technically, the affinity of a PDB to a database instance in the RAC cluster is defined by opening the services of the PDB in that instance. What about the other nodes? Basically, each PDB is visible in every node of the cluster. However, in nodes in which it is not open, it will be seen in mounted state, which is about as closed as you can get. And with this configuration, we've got a pretty nicely balanced cluster. The resource meters on the right here show a comfortable load on each node. So far, so good. But now, let's add a couple more PDBs to the cluster. We'll open PDB 5 in node 1 and PDB 6 in node 2. Now our cluster is beginning to look a little overburdened, with both resource meters now in the red zone. To address this problem, we'll expand the cluster by adding an additional node running a third instance, instance 3. Now we can do some load balancing by redistributing the PDBs across the newly expanded cluster. This is a nice, simple process. In fact, it can be done either by using servctl or via SQL, using an alter pluggable database relocate command. And the result is that once more we see a nicely balanced load across our cluster. So far, we've seen what is described as singleton affinity. In other words, each PDB is open only in a single instance and present only in mounted state in other nodes. It's also possible for a PDB to be open in more than one node, or even all nodes. For example, as we see here, PDB 7 is open on all nodes, and PDB 8 is open in nodes 1 and 2. In general, however, singleton affinity is a very good model to follow, as we shall now see. The tight integration of multitenant with RAC includes a capability known as a per PDB lock domain. This provides strong isolation of a PDB's data and locks to the node or nodes in which it's open. So, as is shown here, with PDBs 1 and 2 affinitized to node 1, PDBs 3 and 4 to node 2, 5 and 6 to node 3, and 7 and 8 to node 4, we know, for example, that only the SGA of node 1 has any data or locks to do with PDBs 1 and 2. Therefore, we know that in the event of a node failure, Cache Fusion need not consider any data or locks for PDBs not open in that node. The benefit is twofold. The affected PDBs recover faster on the surviving node, and the brownout experienced in other PDBs in surviving nodes is significantly shorter. To illustrate the high availability characteristics of a CDB cluster, let's see what happens when one of the cluster nodes fails. Here we see a 4-node cluster and 12 PDBs distributed across the cluster with singleton affinity. With admin-managed services, this primary affinity would be defined by specifying the PDB as preferred in the node with which it has affinity, designated here with a P. The A's designate a node in which a PDB is marked as available. This is the node to which the PDB will fail over in the event of a failure of its preferred node. For instance, PDBs 1, 2, and 3 each have preferred affinity for instance 1. To spread the burden of a potential node failure across the cluster, each of these PDBs is marked available in a different node, PDB 1 in instance 2, PDB 2 in instance 3, and PDB 3 in instance 4. The M represents the mounted state of each of these PDBs in the other instances. What happens when instance 1 fails? Each PDB that was open on the failed node fails over to the designated surviving node. In this video, we've seen the close integration between multitenant and rack. We've seen how a PDB's affinity to a node in the cluster is defined by opening its services there. We can elastically adjust to changing workloads simply by changing the affinity of PDBs for load balancing purposes. Most relevant to our theme of high availability, we've seen how effectively the surviving nodes of a cluster can absorb the additional burden in the event of a node failure, with per PDB lock domains minimizing both the outage in the affected PDBs and the brownout experienced in the surviving nodes. In this section, we discuss the snapshot carousel. This is a repository for periodic, point-in-time copies of a PDB. For example, we might take nightly snapshots of a particular PDB. It makes sense to limit the number of historical snapshots we take. Perhaps we only need snapshots for the past week. The maximum number of snapshots to be retained is configurable. The default is 8, which is also the highest value that is currently supported. Every 24 hours, at midnight, we drop the oldest snapshot. You can think in terms of the carousel rotating by one slot. The newly vacated slot becomes the slot for T0. A fresh snapshot is taken, and this is dropped into slot T0. The process repeats the following midnight, as the calendar flips from Tuesday to Wednesday. And again from Wednesday to Thursday. And Thursday to Friday. The snapshot carousel can be very helpful for debugging date-specific problems. For example, we might have a problem reported on Friday. It's a new problem, which seems to be data-related, and arose earlier in the week. However, the report is not specific about the exact date on which it was first encountered. We might try a bracketing approach. Take clones from the snapshots from Monday, Tuesday, and Wednesday, and run tests to see whether the problem shows up. The problem was not reproducible on Monday, so we can eliminate that date. Further testing shows that the problem shows up already on Tuesday. Therefore, we can eliminate Wednesday too. We now drill into Tuesday in more depth. You'll notice how agile this process can be. These are the sorts of capabilities that modern, cloud-based development organizations require, so that they can keep up with the demands of the modern business climate. Technically, snapshots can be materialized either as full clones or as snapshot or thin provision clones. Another great use case for snapshot carousel is as a convenient source for simple point-in-time recovery of a PDB. Let's say a few days go by uneventfully. Business proceeds smoothly, and snapshots are taken automatically every midnight. But then, on Wednesday the 28th, we discover that a serious data error was introduced the previous day, Tuesday. It is determined that the simplest remedy is to recover from Monday's snapshot taken before the data error was introduced. We simply drop the current PDB and restore a clone of Monday's snapshot before the data error was made. In this section of the presentation, we'll review various backup strategies. A sound backup strategy is, of course, a fundamental element of any HA system. A very basic backup strategy is to take periodic full backups. Perhaps you do this every Sunday at 2 a.m. At least you've got a backup, but it's a pretty primitive strategy. In the event of a failure, the recovery point, RPO, would therefore be the previous Sunday at 2 a.m. Weekly full backups, combined with retained archive logs, enable point-in-time recovery to any time during the week. That's a far better RPO than is achieved with the weekly full backups alone. However, recovery through several days' worth of archive logs can be quite a lengthy procedure. Therefore, the recovery time, RTO, is in general relatively poor with this strategy. So with good RPO but poor RTO, we might pronounce this strategy as tolerable. An established best practice with RMAN-based database backups is shown here. We have periodic full backups with regular, incremental backups taken at intervals in between. A typical model is to take weekly full backups, perhaps Sunday at 2 a.m., and then daily incrementals, perhaps taken at 2 a.m. on every other day of the week. Archive logging is also enabled. This is indeed a very respectable strategy. It delivers good RPO, since pitter to any point in time is possible, and it delivers good RTO, since restoring from a full backup, then applying the required incrementals, and then recovering from the archive logs to the required point in time is a very efficient strategy. This slide illustrates a point-in-time recovery. In this example, we're using a typical backup strategy involving weekly full backups and daily incrementals. Let's say that at lunchtime on Thursday, we decide to recover to 10 a.m. on Tuesday. That's what you tell RMAN to do. What RMAN does behind the scenes is to restore previous Sunday's full backup, apply incrementals from Monday and Tuesday, and use archive logs to recover from Tuesday at 2 a.m. until Tuesday at 10 a.m. So far, so good. But what happens if the PDB I'm recovering had been moved between CDBs since Sunday's full backup? For example, this might have happened at noon on Monday. Here I provide a little historical context. This is more relevant for those with experience of prior releases of Multitenant, but may also be of interest even if you're looking at Multitenant for the first time. In prior releases, to achieve the same point-in-time recovery, at lunchtime on Thursday we decide that we want to recover until 10 a.m. on Tuesday, the pitter was still possible, but more complicated. You would restore to an auxiliary instance, recover to the point before unplug, manually move the data files to the new CDB, roll forward to the desired point in time. In practice, this additional complexity could limit the agility of moving PDBs between CDBs in previous releases of Oracle Database. The transportable backup feature, now available, eliminates all the additional complexities associated with a pitter in a situation where the PDB in question had been moved between CDBs since the last full backup. The point is that, with transportable backups, you can perform a PDB pitter to a time after a PDB has been moved, but before the next full backup. This works whether the PDB has been moved via unplugged plug or online PDB relocation. In this presentation, we've covered various important high availability considerations that apply to Oracle Multitenant. Having briefly reviewed the architecture and its benefits, we discussed PDB lifecycle management, the nuts and bolts of hot clones, integration with DataGuard, refreshable PDB switchover, integration with Oracle Real Application Clusters, snapshot carousel, and transportable RMAN backups. Armed with all of these technologies and techniques, you can truly make your multi-tenant configurations rock solid.